K and open a function to the field on U and a point in U. Now, phi is analytic at X if we have the following. First of all, or maybe I'll say it in words and then write down. Phi is analytic at X if there exists a neighborhood, a polydisk neighborhood of X, in which phi is given by a converging formal power series. Okay? So here is it. R will be the radius, or the multi radius of this thing, and G I'll take to be the formal power series. So I want to converge in that polydisk such that, well, first of all, I want these to be included in U. So this is the polydisk centered at X. This is the shift of the polydisk. And now I want the function phi to be the same as G up to this shift. So phi and over y in X plus I have phi at y is the same as G at its shift. Okay, so this is an analytic function to the field. Now, if phi is this is a function to k to the m, or maybe to v inside k to the m. This guy is analytic if each phi is analytic at each x. So I have the notion of analyticity at the point, and the notion of the function is analytic if it is analytic at any point. Now, so far I want to emphasize that, well, maybe I should ask. Okay, can you give me an example of an analytic function? Polynomials are certainly analytic functions. Another example?
Analytic function.
This is not an example of an analytic function, although
I'll see.
okay, so what we want to emphasize is that so far, of the general fields, we don't know even if the function that are supposed to be analytic, like converging functions in some, this guy G here, which is a converging function in some polydisk, we don't know that this is analytic in the polydisk. Okay, because we don't know that it can be represented as a power series in points other than 0, if I shift it. I need to prove something. This is easy, or it is not so hard, but there is something to say. So this is what I want to say, and for this I'll give the following definition. So I'm defining a certain operator on the space of formal power series, depending on the multi-index beta. So, for formal power series F and the multi-index beta, I'm defining delta beta of F to be the following power series. Instead of the coefficient A alpha, I'm taking A alpha times alpha beta. I didn't finish, but let me just explain what alpha over beta is. Recall those are multi-indices. So this is, as you might expect, this is just a. So now I'm taking, beta is fixed, so it makes sense here to go over alphas which are more than beta in the multi-index sense. So this is component-wise. I'm summing over all these and taking the powers here of the difference. Again, you understand what alpha minus beta is. And this is the product of xi to the power alpha I minus beta I. And again, these are the coefficients that I'm taking.
What is alpha over beta I unless they're integers and then it's obvious?
What is? What is the question?
The multi-indices don't have to be integers.
No, they need to be integers.
Understand? Sorry.
My indices are always alpha and beta here are always in.
And oh, sorry. Okay.
Okay. So the following lemma will explain why those guys are needed and what are, I'll tell how to deal with those. If F converges, so F is a given from a power series as usual. F is convergence in P0S. And maybe I should make it a mark. So usually formal power series are given by F, sometimes G. For some reason that will appear in the future, I choose here G. And I'm using the symbol S here and not R. It doesn't matter for me, right? But it makes sense for me. Then, okay. So this is a new formal power series, and the claim that it has the same domain of convergence. This is one. Two. Now, fix X in that domain. And now, delta beta of F at X is defined. This is a number in my field. This is an element of the field. So I can take these, X is fixed. This depends on beta. I can take these to be my coefficients. Little x, big X. And this is a new formal power series. And again, the claim it converges in same domain. 3. Now, fix S, fix age now. I want to think about it as I want to think about X plus age. Age is some shift of X. And I want the shift to still be in inequalities. So I want to be S times X. And again, now I think of X as a multi-radius. So is clear what this is? So this is S1 minus X1. X1 is a real number, and which is smaller than X, smaller than S1, right? Strictly smaller than S1. So this defines a new polydisc. So here is 0, here is my polydisc, and here is X. Here is the new polydisc. Well, I guess that page is here. But I want to think about X plus 8. Where am I? Okay, so for all X, for all such H, then here is my remark that I just said. X plus H is here. There is no content here so far. And now I can, since it is there, and since this power series converges here, I can apply this function. So f is defined here, so I can apply it to this number, x plus h, but I can also apply this function. And the claim these two are equal, and there is a name to this. Go down to the name. Now I have to prove. Yes.
In the second one, converges in B0 of S or B0 of S?
B0 of S.
Okay.
Thanks. Sorry. Yeah. Okay. Someone is reading. And yes. Excellent. Now. Okay, so let me, as usual, I don't want to work with S, I want to work with slightly smaller guy, so I can work with closer polydisc. So I'm fixing T less than S, and now pick somehow smaller than S minus H. All those guys are tuples, right? Don't forget that. Now, let me write down the following sum over alpha, and here I will have a finite sum. I will sum over all beta less than alpha. So this, the second sigma is a finite summation. So there is no problem here. And I will now take A alpha, alpha beta, absolute value of that, up to the beta. And I want to evaluate this. So these are real numbers. So this is standard real analysis that we're doing here. trying to estimate this infinite summation on that index. And again, everything is positive, so there is no nothing is happening. So please tell me what is the non-trivial thing that I'm doing here, or not entirely trivial. So first of all, I'm taking absolute value here, and now I'm taking alpha beta and copying those values. So why did I write inequality here and not equality?
Because those are integers.
So this is an integer. So alpha beta is an integer, and I use the obvious inequality here. Okay? But now, of course, this A alpha step outside, and here I have just a usual binomial thing, I mean, multi-binomial thing. Again, coordinate-wise, I have the binomial thing, and altogether, this equals. So over alpha, A alpha of t plus r to the alpha. And now r was chosen such that t plus r is less than s, and s was chosen such that we have convergence in P0s, so we have actual convergence, absolute convergence for every smaller guy. So this is like a thing. Fine. So this positive sum is finite. Well, this infinite summation is finite value. So in particular, we can torture it and we can rearrange the order, right? So I will get that this is I'll sum over beta first. Now and then over all alphas, which are bigger than beta, this is double infinite summation. No. Or maybe let me take the alpha of the beta here before. Now this is again, as I said, an infinite sum. And now I have A alpha, alpha beta, T alpha minus beta. And as I said, this is less than infinity. And this is true for every such R. And since R typically I can choose R bigger than 0, all those things for every beta must converge, all those sums. This is for every beta. Now what am I closing here in brackets is exactly these coefficients, right?
Alpha minus beta.
Alpha minus beta. Yeah. Oh, sorry, but T. Maybe let me just to make it clear. So this is less than infinity, and to make it clear, let me write it like that. Delta beta f at t. this is exactly what I needed to show, you know, to this guy converges. This happens for every t smaller than s. I show that this is if you read it later on. This, this implies that delta beta. Yes.
What does this mean? That's a function and that's a form of our solution.
Converges.
Oh, yeah.
Okay.
He is converging in. Yeah, I really forgot.
Thank you.
And there it's P. There it's P0.
Sorry?
It's P. It's the close point.
Now we're good.
Sorry. I guess I should have made some notation to something is converging in this and that. Okay, where are we? So this is one. Not two. Okay, now I'm fixing x in P0s. Right, this is the all thing here, and I'm specializing whatever happened there to this t. T will be x. That will be because whatever I did here. Previously I fixed this t. Now we'll take this x to be my t. Everything that is written on that board, of course, applies. And also I will fix r, which is smaller than as previously. Okay, now sum over beta now this is defined as we observed in one, and I can write down this thing, and now let me just rewrite it.
Now it's small x.
Right, small x. Very confusing. Close bracket, close this. Now, do the triangle inequality. let me write down. This, and I got myself confused. So I guess this should be written here. I guess this is this line. T is X, just synonyms. I use the triangle inequality to put the sum, the absolute value inside, and then I apply it to this. I mean, then I have this times that. Apply it to this, apply it to that, and got T. And then I got this term over there, which tells me that this is finite. So this gives me the finitude of this over here, which is exactly, I guess, what I needed to establish right here.
Okay. How can you use the triangular inequality? The sum is infinite.
Exercise. Okay, lastly, now I will prove 3. So, same style. Get some space. Okay, now I want to write down this equation over here. So, I'm looking at f of x plus h with such x and h, and I'm writing explicitly what do I have here. Now this is just a formality now, but let me do it. I'm using the binomial formula. And now, this equality sign should be justified. As I said, nothing is completely trivial, but this was justified when we observed that this thing over here is finite, so I can rearrange things, etc., etc., etc. So I'm applying it now. I should say, I'm applying this shuffling thing not over the rails. I'm applying it over the. Now I'm reshuffling. I'm doing forbidding, and I'm doing it in the field K, not in the rails. So I'm using these terms that you know that you can do it for absolute convergence series over the rails, and I'm claiming that the same proof and the same thing holds in K, right? And this, I guess, is clear. Just I want to emphasize this. So of what? Of A alpha, alpha beta, x alpha minus beta, h beta, which is by definition sum over beta of this thing. And this is okay. And by this I prove the length.
Definition of delta beta has absolute value.
No, definition of delta beta, it does not appear on the board. No, but
That's the definition.
Okay.
this, yeah.
Okay.
Ignore the sum. This is the definition. Okay, raising. I'm done with the proof. So, So again, delta beta, we could think of it as an operator on the space of formal power series. And actually, as lemma 1, I guess, shows, it's an operator, it's a well-defined operator on the space of converging in a given polydisk formal power series. Now, we are happy because, okay, in the beginning of this hour, I defined the notion of analytic functions, and I claim the following. If f converges in P0s for some s, then f is analytic. Okay, so I need to show that f is analytic at every point. So, unfortunately, shall I write down the definition of analytic at the point? Just, or you remember it? You remember the definition of analytic? So, let me just say it. So, at every point, I want to establish a polydisk around it, such that f coincides with a converging formal power series at this polydisk. So, so the polydisk that I will take, that will be the R polydisk, and R will be, I mean, actually I can take the maximal that fits in. So R will be taken to be this thing. This is the maximal radius, but if I shift it by x, it fits inside P0x, right? Like this now, then x plus z. And now I use G when I make the definition for the formal power series. What will be the formal power series? This one. So G will be sum over beta, delta beta, fx. So this is defined by lemma 1. Again, x beta. And it converges in P0R by lemma 2. Right? And it satisfies the required equation by lemma 3. I'm writing it down now. For y, in this shifted ball, x plus P0R, we have, maybe, let me be explicit. For this h, being the difference, y minus x. So this is, as you see, in P0R, we have, well, we have that this is in P0R, hence, by lemma 3, f of y, I guess, it's not the deep part, this equation, but now this is g of h, or maybe I'll copy this. This is sum over beta, delta beta, f at x, h to the beta, which is g of h, which is g of y minus x, and this equality is what was needed in the definition of an analytic. Okay, we're happy. So when we study the definition of analytic functions, again, this is not void. I mean, we have plenty of those, all the converging power series. In particular, well, we know the complex numbers. We know that there are a lot of converting formal power series, but also over the p-adics or other non-Archimedean fields, I have plenty of those. Whenever a completely algebraic condition, whenever I have coefficients in the number field, sorry, in O, whenever I have coefficients in O, I have convergence, easily. So, you're very happy. So we can start. Okay, so here. So we have phi u to be analytic. This sits in some kn, this sits in some kn, open. A linear map. I'm defining now the notion of derivative. A linear map from Kn to Kn is the derivative, or maybe I have x in u before is the derivative of phi at x if, well, you write it down, as you know. It's the same definition that you have. I'm shifting the function f, and I want it to be no. Please be reminded that the absolute values are coordinate-wise. Okay, and I want this to be name of that when h goes to 0, but h is not 0. I want this, so it is defined. I want this to be 0. This limit. So if we have this, if we have a good linear approximation of my function phi at the point x, then I'm saying that phi is differentiable at x, and that this guy here is differential, the derivative of x, of phi at x. Same definition that you would give. Observation, the derivative, I'm calling it the derivative because it is unique, it exists. Actually, it does exist. Analytic functions are differentiable. This will come in a minute, but what is it? What is just an observation is that it is unique. If you have two, then the difference between M1 and M2 kind of spoil everything. You can have zero. This is, again, an exercise. And denote df at x. So, just to be clear, this is home of vector space, K vector space, from K and Kn. Oh, n by n matrix. And obviously, if we shift x to be 0, and we shift maybe we could also shift f of x to be 0, then the power series it does not have a constant term, and its linear part basically will be that derivative. It's more or less obvious. So let me just write it down. Theorem. The derivative of an analytic function exists, or analytic function f exists, and df now, if it exists, so this is at every point. So df could be seen as a map. This is u to v. Regarding the same function. Oh yeah. I guess that I called it phi and f. So. So I mean this function. This is the same function I'm discussing now, and its derivative exists at every point of u. So it gives me a function from u, if it exists indeed, it gives a function from u to on km. Now this is an n times n vector space, so I can discuss analyticity of this function itself. So is an analytic function, or is analytic. So derivative exists and from an analytic function itself. So the second statement or maybe no. So this is one. Here's the second statement. So f now this is a function into k. A priori this phi was a function into k to the n. I'm taking just one coordinate of phi maybe, which converges in P0s. What is d of f? And I'm giving it coordinate. So this should be, it defines, this is an n value. So this should be a function from k to the n to k. So it should be given by, so this should be a function, right? So, or if you wish, it will be given by a row vector. And what will be the coordinates? I think we understand very well. This will be the directional derivatives of f. So if you wish, we have notations for those. precise. This is from U to home to make it stop. Precise. I mean, this thing here depends on x. U, I guess, should be 0. So this statement here is very similar to that, but it's actually interpretation in coordinates. So if I have f, and now I'm just taking one guy, so phi was an m tuple. So here I'm taking just one guy, and I'm saying that now E1, you understand, this is the multi-index 1, 0, 0, 0. This is the multi-index 0, 0, 0, 0, 1. So this is, let us remind ourselves. Me remind myself. So this is some alpha more than E1 of A alpha, and here there was supposed to be alpha over beta. Beta is E1, so this is basically this is alpha I, right? Alpha is alpha 1, sorry. Alpha other alphas, alpha 2 is sorry, beta 2 is 0, and beta 1 is 1. So this is alpha 1 over 1. Okay, sorry for maybe I'll rearrange it. So that x alpha minus 1. Again, so this is explicitly directional derivative in direction E1. Okay. So the theorem that I stated that these two parts, but actually, as you can see, the second part, which is local in nature, which is in coordinates. The statement is local in nature. Second part is in coordinates, and it implies difference. And itself, it follows directly from the following factors. I can present fx plus h as f of x plus first terms. And now I want to write down, basically I'm writing this. Fx is the beta equals 0 part. This now here I will take betas of degree 1. And here I will have higher terms. So here, is it clear what is the degree of beta? Sum of the components. So, using this notation for the first time. That's what it means. So this is an expression of f and so the proof directly follows.
It's 6 point. Talk about this session.
Yes. Let me just see if this is logical place to. No, I just want to finish something, so I will not to start it. have one more sentence or two to make, and then. Okay, let me make a remark and stop. Sorry for this extra time, but it fits here. So df at ei, so df, this is the f, and so for a given x, at ei is the same as delta ei f, as I said. Ei is an element of k to the n, right? Sorry.
dfx. Yeah. EI.
Yeah, I'm trying to omit the x. How? Maybe. Okay, maybe I'll just say it enough to at this time. I'm getting confused with my own notation, and probably you might be as well, and this is enough already. So I just want to say that those guys here are just, I can view these, as I said, as operators on this space, and actually those operators commute, and those defines, I can think of this as E1 maybe, the derivative of the odd direction E1, and the formula for delta beta involved with some what I want to say is the following. Those are commuting operators. This is to see, and by success, by the composition, I can define what d alpha is. Can define by iteration the operator d alpha, and so probably this is d to the alpha I. E1 done alpha 1 times, and those operators, they don't commute. So they give a nice algebra of operators, and d alpha times d beta is actually d alpha plus beta. And the alpha, if you think of it, is just alpha factorial times delta alpha. And lastly, it follows, but you can actually prove it by inspection. You have the following result about composition of those operators. And this is the formal identity. I mean, applies I mean, you don't need conversion in order to do this. So these are just remarks that I want to make at this point. I don't think I will ever use it, but this is something that you need to know. I mean, there is this interesting algebra of differential operators, formal differential operators here, which are given by basically those, and also they apply for converging series. Okay, so I'm done. I'm very tired. You can leave, but also we can discuss the hour, or maybe we already got